All right, this video is going to cover notes 7.3. We're looking at proving triangles similar. So to start off, we just want to review, when we're looking at similar triangles, these have corresponding angles that are congruent. And when we're looking at corresponding sides, the corresponding sides are proportional. So very, very important that we understand this part here. So just reiterating, when we're looking at similar triangles, the corresponding angles are congruent and your corresponding sides are proportional. So we have three theorems that allow us to prove triangle similarity. The first one we're going to look at is known as angle-angle similarity theorem, otherwise known as AA. So what this theorem states is that if two angles of one triangle are congruent to two angles of a second triangle, then the triangles themselves are said to be similar. So for example, if we were to take a look at the two triangles that we have here, we can see here that angle C is congruent to angle F. So if C is congruent to F, and we see here that A is congruent to D, then what we have here is two pairs of angles that are congruent in two triangles. That's enough for us to say that the triangles are similar. So for this similarity statement that we have here, we get to decide the order. In this case, I'm going to say triangle CAB would be similar to, well, I started with C. C corresponds to and is congruent to F, so then I have F. A corresponds to and is congruent to D, so the next letter would be D. And then lastly, E. So when writing that similarity statement, just be mindful of the order in which you're writing it. So that's angle-angle similarity. Again, you just need two pairs of angles congruent in two triangles in order for us to say that they are similar. So if we're to take a look down here, let's look at some examples. It says, can these triangles be proven similar by the angle-angle similarity theorem? If so, write a similarity statement. Well, if we take a look at the first example, what we should see here is two triangles. We have a small triangle here in yellow and a larger triangle here in green. So we're checking to see, hey, do we have angle-angle similarity? Do I have two pairs of congruent angles? Well, I see here that we have 52 and 52. Well, that takes care of one pair of angles. And then I also see here that if you look at the yellow and the green triangle, they both share angle A. So that is called a reflexive angle. So that would count for our second pair of angles that are congruent. So because we're able to check that checklist there, we say that these two triangles would be similar by angle-angle. Now, they're also asking us to write a similarity statement. So if we're going to write a similarity statement, then we can say triangle, and we'll go ahead and name the yellow triangle first. Let's call that triangle ABE. So triangle ABE would be similar to, well, triangle ABE, we started with the angle A, which is present in both, so A, and then B here would correspond to C, so CD. So this is the green triangle, and the first one was the yellow one. So we're writing a similarity statement whenever the triangles are similar. If the triangles are not similar, then you cannot write a similarity statement. So let's take a look at the next one. If we take a look at the second example, I see here that angle K has one ring, and in the other triangle, I don't see an angle marked with one ring. So what we're checking for is, do we have angle-angle? I do see here that we have vertical angles present here. So I'm going to mark this with 4 rings. It seems kind of excessive to put 4 rings, but I already have one angle marked with 1 ring, an angle with 2 rings, and an angle with 3 rings. So we have to use 4 here. So that takes care of one pair of congruent angles, but it remains to see that we have a second pair. So we do not have a second pair of congruent angles. In this case, the triangles are not similar. And then we look at the next one here. The next one, again, we end up seeing that we have vertical angles here. So for testing for AA, I like to write it out off to the side and then think of it as a checklist. We have one pair of congruent angles there marked in blue. And we see here that angle J is congruent to angle F. So that takes care of a second pair. So that checks the criteria for similarity by angle-angle. So we say these triangles are similar by AA. And we'll put that little squiggly sign there and in the previous or first example that we saw. So the answer is that they are similar. Let's write a similarity statement. We can say here triangle, and if it's up to you to write it, the order in which you write the similarity statement is totally up to you. Just be consistent. I'm going to start with this first triangle on the left, and I'm going to go in the order of the angles. I'm going to go JHK. So JHK would be the first triangle that would be similar to, well, the second triangle would be triangle FHG. And so there are some examples of angle-angle similarity. Now, what we also want to make sure that we understand is that similar figures can be used to find lengths involving using the properties of similar triangles to measure heights, lengths, or distances that are too great to be measured directly. For example, if we wanted to look at the height of the school, right? We're not going to go to the school with a ruler and start measuring that way. We can use similarity for that. So if we look at example one says a flagpole casts a shadow that is 27 feet long. At the same time, a man who is 6 feet tall is standing nearby and casts a shadow that is 9 feet long. How tall is the flagpole? And the hint here is draw a picture. So let's focus on the first sentence. The first sentence is talking about a flagpole. So we have a flagpole, and they tell us that a flagpole casts a shadow that is 27 feet long. Well, if you're thinking about a shadow, think about you standing outside in the sun. Where is your shadow? Your shadow is typically going to be found on the ground. So the shadow that is being cast here is going to be on the ground, represented by this blue line. So we know that that is 27. And it says, at the same time, a man who is 6 feet tall is standing nearby and casts a shadow that's 9 feet long. Well, the title of the notes here is proving triangles similar. So why don't we go ahead and make this flagpole situation a triangle by connecting the top of the flagpole to the end of the shadow. Now, if we look at the second part here, it says a man who is 6 feet tall. So let's go ahead and draw a man here. This man is 6 feet tall, which would be the vertical distance here, is standing nearby, and he casts a shadow that is 9 feet long. So this person has a shadow that is 9 feet. And we'll go ahead and make this a triangle also. We're assuming that both of these individuals, well, I guess the individual and the flagpole, I should say, are standing perpendicular to the ground, meaning that we have a 90-degree angle here. And they want us to find how tall the flagpole is. Well, that would be represented here by x. Well, what we have here is a situation of similarity. And if we're going to solve for x, the height of that flagpole, then we can look at setting up our corresponding sides. Well, the height here would correspond to the height of the man, and the shadow of the flagpole would correspond to the shadow of the man. So this can help us set up a ratio, and specifically a proportion. If we were to look at finding x, I can say x over 6, which would be the height over the height, or yellow over yellow, would be equal to the shadow over the shadow, which would be 27 over 9. From there, we cross multiply. If you cross multiply, 9 times x is 9x. And then if we take a look at 6 times 27, 6 times 27, I can run that in the calculator real quick and check to see. That would give us 162. Dividing by 9, we get that x is equal to 18. So what we see here is we get x to be 18. So now I know that this is 18, and they asked how tall is the flagpole? Well, it's 18. 18 what? In this case, 18 feet. So there's our answer. All right, moving on with our notes here, we have now the second similarity theorem that we're going to look at, which is side, side, side. So this states that if the corresponding side lengths of two triangles are proportional, then the triangles are similar. So in this case, what that would indicate here is that if we're looking at these two triangles, and this is going to kind of represent our first example here, looking at the two triangles, how am I supposed to identify what sides are corresponding? Well, if you look at triangle DEF, I see that 12 is the smallest, 18 is the medium, 24 is the largest. In triangle ABC, 4 is the smallest, 6 is the medium, 8 is the largest. So if we were to look at this, then we can identify here that the way I like to kind of write this out is, well, I'm going to just set this up as small over small, medium over medium, large over large, which if I were to plug those values in, my small over small, if I decide to start with triangle DEF, I'd be doing 12 on the top. So small over small here is 12 over 4. Medium over medium is 18 over 6. Large over large would be 24 over 8. And if you end up simplifying those, you get 12 over 4 is 3, which would be 3 over 1. 18 over 6, 3 over 1. 24 over 8, 3 over 1. So what we're seeing here is that all three ratios for the corresponding sides are proportional. So with all three sides, the reason why I put the little check marks there is because I treat this as a checklist. I have three ratios that are equivalent, so three sides that are proportional checks off all three S's, allowing us to write a similarity statement. In this case, let's say we have triangle DEF. Now that triangle DEF, to identify how to write that second triangle, well, look at point D. That angle D is connecting the small and the large, so that would be small and large over here with A. If I look at the next letter in my similarity statement, E connects the small and the medium. Small and the medium would be B. And then you have one remaining letter left, which would be C. I know here it's pretty obvious how to write the similarity statement, but sometimes they'll rotate the figure, they'll flip it. So use those markings to your advantage when writing that similarity statement. All right, so next we have example 2. Just look at another one here. It says, can these triangles be proven similar by the side-side-side similarity theorem? If so, write a similarity statement. We're going to use the same process here. If we're using the same process, my small, medium, large, and in the second triangle, small, medium, large. So just because you have three sides in both triangles doesn't mean it's automatically SSS. You have to go through and check, are all three sides proportional? So if we were to do small over small, we would be looking at 3 over 9. So 3 over 9 is equal to, then medium over medium is 4 over 12. Large over large would be 5 over 15. Now if we're to simplify those, 3 over 9 is 1/3. 4 over 12 is 1/3. 5 over 15 is 1/3. So what that represents for us here is three sides that are going to have the same ratio, meaning that three sides are proportional. That means I check off three S's. We are good there. These triangles are, in fact, similar. So yes, they are similar by the similarity theorem SSS. So we'll typically write that like this. And then we write the similarity statement, which we will say here, triangle, let's do STU. And that would be similar to triangle XWV. I think we spent enough time kind of discussing the order of writing the similarity statement, so we'll just go ahead and go through that process here. Now, the last way to prove two triangles are similar is by side-angle-side similarity theorem. The way that this works is if you have an angle of one triangle that is congruent to the angle of a second triangle, and the lengths of the sides that include these angles are proportional, then the triangles are similar. So kind of rewording that so that we understand, how do I identify that we have side angle side? Well, you have to have the angle in between two sides, and the angle in between those two sides need to be congruent in both triangles. And the two sides that you have, the two pairs of sides you have, must be proportional. So what that would look like in this case here is if I wanted to check side angle side here, I would need to have the angle in the middle of two sides, and I would need to have those angles be congruent, so 53 and 53. That checks off the A because they're congruent and they are in between two sides. Both criteria must be met for you to check off the A. So the kind of information we have off here to the left is going to not really be helpful for us here because there is no angle C. And we, again, don't have C. So what we'll do here is we'll write this off to the side. What we actually have here present is that angle Y is congruent to angle E. And then our sides that we have here, well, between 6 and 10, the smaller one here is 6. And between 9 and 15, the smaller one's 9. So if we end up seeing that we have 6 over 9, for this to be SAS, that small over small would have to be proportional to this, we'll just call it large over large, which would be 10 over 15. Now, if you were to simplify those, what you would end up with is 2 over 3 is equal to 2 over 3. And that right there is two pairs of sides that are proportional. So two sides having the same ratio tells us I can check off the two S's. So what we have here is SAS. This is how SAS works. So we'll look at one example real quick. The example here is asking, can these triangles be proven similar by the side-angle-side similarity theorem? If so, write a similarity statement. Well, if we are going to do this, and I should have done this for the previous examples, let me start doing this every single time. You first want to identify what are you checking for. Well, they're telling you to check for side angle side, so I'm going to write that off to the side so that I treat that as a checklist. Now, the first thing I check for is my angle in between two sides? Well, if we take a look here, the 120 is in between the sides measuring 4 and 6, and the 120 over here is in between 6 and 9. So we do have the congruent angles in between two sides. Now, all that's left for you to check is the corresponding sides. Are they proportional? So if I look at 4, 4 is the small, that goes with 6. In the first triangle, the 6 here is the larger one, which would correspond to 9 in the second triangle. So if I were to set up a ratio to check for proportionality, if I do small over small, I'm looking at 4 over 6. Large over large, we're looking at 6 over 9. And if we were to simplify, what we're looking at is 4 over 6 becomes 2/3. 6 over 9 becomes 2/3. So this is two ratios that are equal, two side lengths that are proportional. So the S's get checked off. We have cleared off the checklist there. These triangles are similar by SAS. It also tells you to write a similarity statement. I feel like we've done that enough times to be able to skip that part. So to keep this video short, we'll go ahead and keep it moving. We have some final examples here now where everything's kind of mixed up and it's asking you to determine if the two triangles are similar. If they are, write the similarity statement and indicate the theorem that proves the similarity. So in part A, what we have here is a situation where we have a triangle embedded inside of another triangle. So I have a small triangle here and then a large triangle here. Now, I didn't do this earlier, but we're going to do this now. What I typically recommend for these types of questions is let's go through and separate out the triangles. If I separate out the triangles, we'll draw the smaller one first. Our smaller triangle here in blue would be triangle KLM. And the side lengths for triangle KLM, from K to L, this is 6. From L to M, this is 10. And from K to M, we actually don't know, so we're going to leave that blank. What we're going to do now is we're going to draw out that larger triangle, which is triangle JLN. Now, if we label the side lengths here, we want to find out what is the length from J to L. Well, from J to L would be from here to here. You would have to combine the 3 and the 6. That would be 9. So this is 9. And then from L to N, 10 and 5 would give you a length of 15. So this length would be 15. So we separate out the two triangles, and this is what we're looking at here. And our ways to prove similarity are, well, we have angle, angle that we learned first. We learned side, side, side. We learned side, angle, side. Well, what I'm seeing right now is I know two side lengths. I don't know the third one, so I cannot use SSS here. I don't know a whole lot about the angles other than the fact that both of these two triangles both share angle L. So I know that angle L will be congruent to itself. So what we're typically going to kind of narrow this down to in this case is going to be SAS. This is what we're going to check for. We have to check for it. We can't just assume it's SAS because I have a side angle and a side. We have to actually check. You got the angle part already down. We understand that the angles are congruent. The corresponding angles there, L. You just have to check the sides now. Now, if we're going to check the sides, what we're looking at here is, well, if we're doing our little ratio, we have the smaller side here with the smaller side, the larger one with the larger one. So small over small, we're looking at 6 over 9. It's equal to 10 over 15. And we get 2/3 is equal to 2/3. Those ratios are equal, meaning that the sides are proportional. So we have similarity by SAS. So going back and rereading the directions here, they wanted you to write the similarity statement and indicate the theorem that proves the similarity. So we indicated the theorem that proves the similarity. The theorem is SAS. That's what I have boxed there in green. But what remains to do is to write the similarity statement. So our similarity statement here that we can write, I'm going to say here triangle KLM would be similar to triangle, in this case, let me draw my large there. The orange one, we would name this as JLN. So there's our similarity statement. Okay, And we will, there's a number of examples here left. We'll hit these here as fast as we can just so that this video isn't crazy long. If we look at this one, whenever you have overlapping or triangles inside one of another, it's typically a good idea to separate them out just to minimize confusion and minimize any careless mistakes. So we got some kind of shared sides going on here almost. So we want to determine if these are similar. So I'm going to separate out this first triangle there on the top, which is this one. This would be triangle EDG. Second triangle we have here would be the bottom one, which is triangle EFH. And then labeling those side lengths, what we have here is 3, 5, 6. From E to G is 6. And then now from E to F, look at from E to F. That would be 6 plus 6, which is 12. And then FH is 6. EH is 10. So as we go through this process, your options to prove triangles are similar are angle, angle, side, 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 angle, side. I don't see anything about angles. I see that I have 3 sides in both triangles, so the one that I'm going to check for is SSS. So if we're checking for SSS, we have to check to see are all 3 pairs of sides proportional. So going through our process here, we got to look at the blue triangle. We have small, medium, large. So your small, medium, large. Over here in the purple triangle, we have small, medium, large, right? So make sure you're taking your time labeling this, so just make sure that we're setting these ratios up correctly. Because if we look at small over small, what we have here is 3 over 6. Medium over medium would be 5 over 10. Large over large would be 6 over 12. Now simplifying each of these fractions, we get 1/2, 1/2, 1/2. That is 3 pairs of sides that are proportional. That takes care of all 3 S's. So similar by SSS. And then if we want to write the similarity statement, we get to decide the order here. If it's a quiz or a test, I'll typically fill out this first portion for you right here. I'm going to call this triangle EDG, that first one. I guess I should color code this correctly. Let me do that in blue. So it'd be triangle EDG. That would be similar to triangle. Well, if you look at E is right here where the large side connects with the small one. So the large connects with the small one here at F. So that would be F. The next letter or vertex we have is D. D connects small with medium. Small with medium here is H. And then the last letter here is E. So I wanted to go through the similarity statement on this one a little bit more in detail just because these are kind of the easier ones to make a mistake on. Like I said earlier, use those markings to help you identify your corresponding parts. Now, if we were to continue moving here, looking at this triangle, what I'm immediately noticing here is, well, we have vertical angles present here. So between our options, we have angle, angle, side, 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 angle, side. Sometimes you can test for more than one, right? You don't have to do testing for all of them, but you have options here, at least for this one. I know all 3 sides in this triangle, and I also know all 3 sides in this triangle. So it's totally up to you. We can do side, 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 or I'm also realizing that, hey, this set of vertical angles is in between 2 sides, so I can check for SAS. I'm going to check for SAS because it's just slightly less work, because I already know the angle part is taken care of. Those angles are congruent because they're vertical, and it's in between 2 sides. Now, what's left for us to check is the side lengths. Are those side lengths proportional? Now, here again is where you want to be careful. Okay, I know sometimes it feels like we're doing extra by labeling it every single time, but it's to minimize mistakes. If I look at the triangle on the bottom, 12.5 is the smallest side. So the smallest side would correspond to the smallest side in the top triangle, which would be 5. So I could set that up already as a ratio. We can do 12.5 over 5. Then if I'm checking for SAS, I'm going to use the 20 now, which is not the medium. That is actually the large, sorry. Would correspond with the large here, which is 8. So if I were to set that up with the ratio being consistent, the 12.5 came from the green triangle. So my value on top of my ratio needs to come from the green triangle again, which would be 20. So I'd be doing 20 over 8, which is my, again, what we did here is large over large, small over small. So from here, what I typically do to check to see are these proportional is I would just simplify, right? And if it ends up being decimals, this would be a good instance to just pull up a calculator. 12.5 divided by 5, if you're not super comfortable doing that, what that ends up simplifying to is, well, that gives you 2.5. If we do 20 divided by 8, well, that's also 2.5. So that means, hey, those two ratios are equal. That means the two pairs of sides are proportional, checking the two other s's. So similar by side angle side. Now, I'll leave the similarity statement for you guys to write on your own. Go ahead and actually try writing the similarity statement and then check with the key of the notes to see if you wrote that correctly, because I do want to get to these last examples on the bottom. Looking at the last examples on the bottom, we got example 5, says name the theorem or postulate that can be used to prove that triangle FGH is similar to triangle JLK, given that angles H and angle K are right angles. So let's go ahead and mark that given in the problem. So they tell us that H and K are right angles, so we're going to mark that with a 90 degree. And what I see here is that that set of right angles there is in between two sides. So the one that we're going to check for here is actually going to be SAS. That's what we're testing for. So we got the congruent angles piece already. We just need to check the sides. So if we're going to check the sides here, we got small, small, large, large. So small with small would be 4 over 3. Large with large would be 8 over 6. Now, if we were to simplify 4/3, well, it's already in simplest form. If I were to simplify 8 over 6, I can divide the top and bottom both by 2 to get, well, 4/3. Same ratio here indicates that these are proportional, telling us that we have similarity by SAS. So there we have it. The question here asked, name the theorem or postulate that can be used to prove the triangles are similar. We got it. It is SAS similarity theorem. So we'll go ahead and just write that little squiggly line that stands for similar. Now, here we have given triangle ABC is similar to YZW. Use the side-side-side similarity theorem to find the values of X, BC, and YZ. So if we look at what we have here, they gave you the similarity statement. So we were looking at finding X, BC, and YZ. Well, BC has X in it, YZ has X in it. We got to start with X. So if we look at BC, BC corresponds to ZW. So these are corresponding. We also see here that we have this side length here, AB. AB is going to correspond to YZ. And then you have one side remaining, so that means AC is going to correspond to YW, right? I recommend color coding it just to make this next process go by a little faster. So if I want to solve for X, I want to set up a ratio that allows me to solve for X. So what I see here in blue is, well, we have 2x plus 3. So blue over blue would be 2x plus 3 over 10. That's equal to, well, now you get to pick. Do you want to do red over red or black over black? Well, if you do red over red, well, now you're doing 20 over x minus 3. Now I got to cross multiply this, which is going to be more complicated than if we were to just choose the other option, which would be, why don't we do black over black? We would be doing 10 over 4. So if we cross multiply here in this case, we're looking at 4 times 2x plus 3. Well, 4 times 2x is 8x. 4 times 3 is 12, so plus 12. And then that's equal to 10 times 10, which is 100. Now, if you were to move the 12 to the other side, you get 8x is equal to 88. Divide by 8. X is equal to 11. Now, we know that x is equal to 11. Doing some mental math here, just speeding this along here. 2 times 11 would be 22, plus 3 is 25. So BC is 25. So mental math here. YZ is the other part they asked for. Well, if it's 11 for x, 11 minus 3 is 8. So there we have it. Now the last part that we have here is, says what method would you use to show that the triangles are similar? Write the similarity statement. So what I would choose in this case is, again, we see vertical angles here. I would check for SAS. Now, if you're looking for this, we got the congruent angle already. I feel like we've done SAS a bunch, but just finishing off this last example. If we're looking at the smaller one here with the smaller one here, the larger one with the larger one. So it really is helpful to label. The last thing I'd like for it happen is a situation where you mislabel and you end up doing 9/30 because these are not corresponding, right? So that's why we label. So if we end up doing this as a ratio, if we do small over small, we're looking at 9/15. Large over large would be 18/30. Now, if we simplify, you can divide the top and bottom both by 3. That would be 3/5. Over here, you can divide the top and bottom by 6. We divide it by 3 here. Over here, we divide by 6. You get 3/5. So those are the same. So we check off SA and the S. So that means similar by SAS, similarity. Now, if you want to write the similarity statement, we can do this in whatever order we choose since an order was not provided. So I'm going to start with C this time. So I'm going to do the first triangle here on the left. Doing that triangle on the left, I'm going to choose this to be CBA. Would be similar to triangle. Well, if I look at CB, CB is that small side starting at the vertical angle. So that would correspond to the small side starting at the vertical angle over here, CE. So this would be CED. So there is our similarity statement, or at least one way we can write it. Okay, like I said, if the order is not specified, you decide that order and just make sure that the second triangle matches. So that's it for the video. I'm sorry for the tons of examples that we have here, just kind of exposing you guys to more problems, vertical angles, things like that, reflex angles. Those are things that pop up again. All right.